All right, welcome back to another problem. Let's get right into it. So we have at this given time, this rod is imparted with the velocity of Vx of 5 feet per second. We have some angle measurements as well as the acceleration that Vx or point X is experiencing from the piston Q. And so they want us to determine the angular velocity and angular acceleration of link YZ. So we have our relative acceleration equations, which you can see I just wrote there. And one of the first parameters we're going to have to calculate is the position vector of y with respect to z, as well as the position vector of y with respect to x, as you can see in that equation there. So you can see that I drew our triangle in our, from our picture, and we could see that for the position vector of y with respect to z, we have the magnitude of that link, or the length of the link, times negative sign of gamma divided by 2. That's for the I hat component, and then plus cosine omega over 2, or excuse me, gamma over 2 for the j hat component. You can do the same kind of thing for the position vector of y with respect to pin x, this time using a length of 2 for the length of that entire rod. And you can do the same thing, calculate that up, and you get the values shown here. So the next step is we want to start populating equations 1 and 2. And because we have two equations for the acceleration of pin y, we can go ahead and calculate. We see that the acceleration of pin z, which is constrained to be stuck to that plate or ground, we can say is just 0. And so what you can see what I'm doing here is, because we are looking to perform a cross product, we need to have some kind of direction assigned to the angular acceleration and the angular velocity. Now we don't know what these are going to be, but because these are plane motion problems, so we're taking place in the xy plane, we know that this rotation has to be pointing in another unit vector direction. So we will just assume it's k hat, and if it turns out that the value is actually negative after we calculate it, then we know that it was actually in negative k hat direction. So you can think of this as being, positive k hat direction being counterclockwise and negative k hat direction being clockwise. So that's the physical manifestation of those directions in our problem. And you can see what I'm doing here now is I'm just populating those two equations now with our givens. So we have, you can see I plug in negative 2 I hat to represent the velocity Vx going to the left. And then you can see I'm putting these equation marks down, or not equation marks, excuse me, question marks, because we don't know what those values are yet. So, we wrote down our equations for the acceleration. However, we still have equations for the velocity. So before I go ahead and write the velocity equations, we'll go ahead and we'll clean up equation 3 a little bit more. So we have the left-hand side of equation 3, and we're performing our final cross product. So remember I call it the cross product triangle, although it's kind of like a flow diagram where I cross j is positive k, j cross k is positive I, but if you go in the reverse direction, k cross j is negative I, etc. So you want to make sure you're being very diligent and very careful with how you're actually carrying out these cross products. And so long as you are, everything should normally turn out correct. So you can see here I try and remember to wrap my unit vectors, so I hat, j hat, and k hat, in parentheses here, just to really make sure I'm on top of everything in terms of my directions and signs. Because you can see what I'm going to do here in a minute is I have these two equations that are equated to each other, and I have components in I hat and j hat only. And so because of that, we know that these components, because equation 3, the left-hand side of equation 3 equals the right-hand side of equation 3, we know that their I hat and j hat components must also equate to one another. And so that's what I'm writing right here, just to simplify it down even more. So now we have equations purely in terms of the angular accelerations that we want and then the angular velocities that we want. But as I was alluding to earlier, we don't know the magnitudes of either of these yet. So currently we have 2 equations and 4 unknowns. So that was for just the relative acceleration equations, but now we can apply the same thing to the velocity. And as you can probably imagine, because currently we have 4 unknowns, 2 equations, if we use the velocity, we're going to get 2 equations, 2 unknowns we can solve, and then we will plug back into equation 3 to get the accelerations. So again, we have Vy is equal to Vz plus omega yz cross r of y with respect to z. You can do the same thing for pin y and pin x. Now I will try and speed this up just a little bit more, so I'll just go right into equating the 2 values together, and using the position vectors that we calculated above, I'm just going ahead and populating these equations here. Oh, yeah, you can see I had to zoom in because I was running out of room. One thing you'll notice with these kinds of problems is some of the math gets very dicey and there's a lot of bookkeeping involved. But again, so we're just going ahead, carrying out our cross products, and making sure we're very cognizant of our signs for I and j hat. We'll go ahead, finish that equation, and then you will see I will employ the same kind of technique where, because we have an equality here, we can go ahead and group terms based upon their I hat direction as well as their j hat direction, just to further simplify. So in I hat, we have omega yz and omega xz, which are unknowns. And then for the j hat direction, we have omega yz and omega xz, which again are unknowns. So 2 equations, 2 unknowns, as we predicted earlier. So I will go ahead and I'll just wrap this up into a matrix form, collecting the scalars in the front. We have our unknown vectors, and then we have our known right-hand side. We'll just do a simple A inverse B is equal to X, and we go find that omega XY is equal to negative 1.22 radians per second, and omega YZ is 3.311 radians per second. So with the negative sign being clockwise, and then the positive sign being counterclockwise. Just to make sense, so we're pushing pin X to the left, so you can imagine that XY is going to rotate clockwise, and then the other one's going to rotate counterclockwise, as we expected. You can apply the same procedure above for equation 3 to get the accelerations, which I didn't do, but just some plug and chug. And I hope this was helpful. Thank you.